So we will be using the number e as the base of exponential functions. I know that sounds weird, but e is actually a special number. And we're going to talk about what kind of number it is, where is it developed from. For the second one, these are the decimals we should have gotten. Also, so there's something special, and this is where e actually gets developed. When you take 1 plus a particular fraction, we call these unit fractions because a unit, 1 unit, is on top, and then the denominator is a different number. But the denominator matches the power. Notice how the denominator in each problem matches the power. Denominator matches the power. Well, if we keep getting bigger and bigger, meaning making this number bigger, so like 1 plus 1 over 1,000 raised to the 1,000. Somebody do that. Take 1, and by somebody, I don't know who I'm going to pick on, but 1 plus 1 over 1,000 raised to the 1,000. Why I had us do this is as we get bigger and bigger, because I don't think our calculators can hold 1,000,000, but as we make this number bigger and bigger, this number actually approaches a certain irrational number. So here we go. Here's what today's about, the number e. It's called the natural base e, or Euler's number, the Euler number. As n approaches positive infinity, so this means as n gets really, really big, as this position gets really big, because that's what we did in warm-up, if we had 1,000,000 or 1,000,000,000 in these positions, e approximates 2.718218, blah, 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 and it keeps going. It's irrational. There's no repetition so far that we know of. There's no repetition in this number. And it can also be found on your calculator. So you should have an E button. When the directions say simplify, that means I don't want any decimals in my answer. I actually just want to clean this up, but I want it in the exact form. So just make a note of that. When it says simplify, I should not be seeing decimals. I'm going to use property rules. So in the first one, so if I'm a coefficient and I just have division or multiplication, notice how there's no plus signs here, no minus signs here. I just treat it like I see it. 24 divided by 8, we get 3. And now let's talk about them e's. So I'm going to take e to the 8th minus 5. This becomes 3e to the 3rd. This is what I want to see. If the directions say simplify and I've got a problem dealing with e's, I want you to end with e's. So let's talk about example 2. So the strategy chosen was to change this negative. The way to change that is put it 1 over 2e to the negative 5x now to a positive 2. So when we change this negative, it moves it as a reciprocal. So just to recap, I distribute the 2. So I'm going to take 2 to the second power, and when I take 2 to this negative 5x, we multiply those powers. I've got something else that's actually not what I want. I don't want that negative exponent. So I'm going to flip it. This means this e to the negative 10x is going to be the only thing that's flipped. The 4 is not being raised to it. So e to the positive 10x will go to the numerator. 4 will stay on the denominator. I could put that 1 in front because I did have a 1, but 1 times anything just stays. Directions change to use a calculator to evaluate. When you see the word evaluate, then I want a number. Now I want a decimal. So we get approximately 20.09. This is what you should be getting if you found the correct button. So if we take e to the negative 0.12 power, we should get 0.886. I don't care where you cut it off. So if the directions are not specific, I don't care where you cut it off, but just make sure wherever you do that you round correctly. Okay, let's talk about these functions that are going to be popping up with e's. A function of the form f of x equals a times e to the, this is rx. So this exponent is rx. R stands for a rate. We're going to be using a rate. This is called the natural base exponential function. Something I want to stress, because with these e's, with these natural bases, it actually, when your leading coefficient being positive or negative, whenever I talk about exponential growth or exponential decay, we're really concentrating on this rate. Is the rate positive or is the rate negative? Because here's the thing. If the leading coefficient is negative, but the rate was positive, it's still exponential growth. If the leading coefficient's negative and the rate's negative, then it's definitely exponential decay. So the leading coefficient being positive or negative really doesn't matter. It all matters on the rate. So maybe make a little star. This matters especially whenever I attack graphing. Because if it's an exponential growth problem, I attack it using the negative 10, 0, 1. But if it's an exponential decay, I switch those signs using a positive 10, 0, negative 1. So let's go to graphing. We're going to graph the function and state the domain and range. So first I got to figure out, is it exponential growth or decay? So because this rate is positive, it's growth. Growth problems should be some type of flat line and then growing. This helps me with my shape. All growth problems look something like this unless your leading coefficient's negative. Then it flips it. So with my t-chart, I plug in negative 10 to get that flat line, 0, 1. If I don't know this shape, if I don't have it memorized, then I might need to plug in 2, 3, 4. So let's graph them. When you plug in a negative 10, you're slightly above 0. We've got 0, 2. And we've got the general shape. General shape is a flat line, and then all of a sudden it gets bigger. We're going to discuss domain, range, and we're going to talk about that asymptote. So we're going to change the decimal and the leading coefficient. This number in this position is positive. That's what makes this exponential growth. So I'm going to attack it like a growth problem, where I'm going to plug in the same numbers as before. Negative 10, 0, 1. I might plug in 2, 3, 4, depending if I need those. Because I have no shifts going on, there's nothing in the exponent, there's nothing out here. When you plug in a 0, you should get that leading coefficient, negative 3. So plugging in a 1, let's plug in those, or plot those points. And let's realize that growth is typically flat line and then increasing, but since the leading coefficient's negative, it's going to go flat line and then down. It's a perfect reflection. Domain. So because we had a negative coefficient, our inequality sign changes. So that means the asymptote is similar to it, y is equal to 0. Now, no homework tonight. We'll continue this on tomorrow.